So I sort of gave a preview as to what independent t-tests were. Previously, we had one sample, and one sample mean, right? One sample statistic that we were interested in. Does this sample mean differ from some hypothesized population value? And I said I didn't really think that those were very interesting questions. More interesting questions are about two means. So the question that we're going to be asking when we're looking at independent t-tests is whether two populations have the same mean most of the time. So these types of questions can take the form of things like this. Caffeine in Coca-Cola and Cola Turca, do they both have the same amount of caffeine? Does Cola Turca have more caffeine than Coca-Cola? Does Coca-Cola have more caffeine than Cola Turca? We don't know. We could buy some Cola Turca, buy some Coca-Cola, take some samples, measure the caffeine levels, and figure out an answer to this question. Is there differences in the impulsiveness of conservatives and liberals? You might think, well, conservatives, they're conservatives, right? So if they're conservative, maybe they're not going to be as impulsive as liberals. Maybe. So you could develop some measure of impulsiveness, give it to a sample of conservatives, give it to a sample of liberals, and see if you're finding different levels of impulsiveness for both groups. Memory scores with and without training, or IQ tests with and without training. Can taking practice IQ tests improve your intelligence, or at least improve your intelligence quotient, as measured by IQ tests? If you want to get into a club like Mensa, have you guys heard of Mensa? Mensa, it's this high IQ society. In order to get into the club, you have to score in the 98th percentile. So you have to be in the top 2% of people scoring on some standard IQ test. Now, there's a caveat. You can take the IQ tests as many times as you want. So maybe if you practice taking a bunch of IQ tests, can you actually improve your performance on the IQ test? So you could give a group of people a bunch of training and another group of people not some training. You take a sample of the one, a sample of the other, both give them an IQ test, and see if there's a difference in their IQs. So these are interesting questions. Most of my research involves questions that are similar to this. Now we can restate all of the above questions as a statement of no difference, right? So the mean caffeine in Coca-Cola minus the mean caffeine in Cola Turca is 0, right? You say that this equals that, you're saying that the difference between this and this is 0. So this is just a statement of a specific difference. In this case, it's a specific difference of 0. Later in this class, we'll show you how you can test other hypotheses too. Like maybe there's a brand of cola. There used to be this brand in the States. It was called Jolt Cola. And their slogan was like 2 times the sugar, 3 times the caffeine. Something like that. Either that or it was like 2 times the caffeine, 3 times the sugar. It was one of those. Anyway, so you could test that. You could see if the difference between those two was what was predicted. Okay, now don't fret. We're going to be doing basically the same thing that we've been doing for almost a week now. There are only 2 new things. Not really new, they're just changes on the old, but it's going to be a little different from what we've been doing before. The new things, we're going to have a new estimate of the population variance. We're going to call this the pooled unbiased estimate of the population variance. We're going to have new standard error. So our new standard error, this is going to be the standard error of the difference between means. So let's take a look at why we're going to need these things. We have a problem. What do you guys think the problem might be? Before we were doing a t-test, we were basing these on a single mean, right? And on a single estimate of the population variance.
So the variance could be different?
The variances could be different. We're going to draw 2 different samples, right? So we could have different variances for the different samples. That's a potential difference, right? In fact, we would expect to find different variances for different samples, right? Because almost never should you draw 2 that are exactly identical, right? So we're going to have 2 means. This isn't the problem. The problem has to do with the 2 pieces of variance that we have. Now, t-tests use one variance estimate to compute the standard error term in the denominator, right? So the standard error of the means that we've been using, this is just the, let me draw it, and then hopefully I will recatch my mind. So our estimated standard error of the mean is simply based on the square root of the unbiased estimate of the population variance divided by the square root of the sample size, right? So we have just one variance estimate here, the square root of that. Now, we're going to need to create a single estimate from our two estimates, right? So we're going to take one sample, we'll give one unbiased estimate of the variance. We're going to take another sample, we're going to get another unbiased estimate of the variance. So we're going to do this, but let's look at a similar question first. Imagine that we want to know what some population mean is, okay? Now imagine that there were two researchers, and each of these researchers was looking at the same population. One of the researchers drew one sample, and they found a sample mean of 12. Another researcher took another sample from the same population, and they found the sample mean was 14. Now, this researcher, having only this information, would say, okay, the population mean is probably 12, right? They could create a confidence interval if they wanted to, but that's their best estimate. Similarly, the second researcher, this is their best estimate of what the population mean is. Does that make sense? Now, we're the third researcher. We come in and we see that this researcher found this was the mean, and this researcher found that was the mean. And we want to create our own best estimate of what the population mean is. Does anyone have an idea how we can do that? Do you have a question?
No, can we combine the confidence intervals?
Potentially we could combine the confidence intervals. Okay, but if we just want a point estimate, if we just want one value, 13. 13?
The mean.
How did you figure that out? You just took the mean of those two things, right? This researcher came up with 12, this researcher came up with 14. So the true mean, our best estimate having both of these pieces of information is just the mean of those. Does that make sense? So each of those is the best estimate the researchers had. The best estimate of the population's mean is 13. This is just the mean of the different means. Okay? Now, imagine that you knew some more information. And you knew that researcher 1, their mean was 12, and researcher 2, their mean was 14, again, just like the previous. But you knew researcher 1 had a sample size of 20, and researcher 2 had a sample size of 10. Which of these two estimates of the mean is the better estimate? This one? Why?
Because the sample size is bigger.
The sample size is big. So what do we know about estimates of means when the sample size gets bigger?
It gets more accurate.
Yeah, this is the law of large numbers, right? As the sample size increases, our estimate of the mean is going to get closer to what that true mean is. And also the standard error of the mean is going to get smaller, right? Because we're dividing by the sample size. So this should be a better estimate, and we know this because it has a larger sample size, and we know what the law of large numbers says. Okay, so before, when we didn't know these things, we just took the one, took the other, added them together, and divided by 2, right? How can we combine these to get a best estimate?
It's going to be 2/3 closer to the first one.
It's going to be 2/3 closer to the first one. So 12 and 14, so this 2/3 closer to 12, so it'd be like 12.33, something? Something like that? How did you figure that out?
Because we combine the 20 and 10.
Okay.
We made 2/3 for the closer, for the first, and just 1/3 to the second.
Okay, so there's this difference. There's like if you look at the total number, right, there are 30 total observations. And 2/3 of those suggest this, and 1/3 of those suggest this. That's really intuitive, right? We have 20 pieces of information for the first, 10 pieces for the second, 30 pieces total. So we can just weight each mean by the number of pieces that we have, and then divide the sum of those weighted means by the total number of pieces that we have. So that's this, right? And I actually came up with a different value, so I'm wondering if I computed it incorrectly. So we have 20 times 12 plus 14 times 10 over 30, right? So I've got this, so that this is 240, this is 140, the total is 380 divided by 30. Does someone have a calculator? Can they do that? Oh, right, because we were predicting before that it would be 13. Yeah, that's exactly right. 13, but now it's a bit closer to the to 12 than it was before, because we are weighting that 12 more heavily because we have more observation. Good? Good. All right. When the sample sizes are equal, this is just the mean of the means like we had before. So imagine that we had two samples of size 20, okay? So we have 20 here, and 20 plus 20. Well, that's going to be 20 divided by 40, right? So this, if we take this part out, that's 20 over 40 times this piece, right? We'll just say that. That's just 1/2 of that piece. It's just the mean of the means. Groovy? Okay. Okay, so we figured out a way to pool our information to come up with a better estimate of what the population mean is. Now we have two variances, right? And we want to create an estimate of what the true population variance is based off that estimate. So what could we do? Notice I said you shouldn't pool unless you assume equal variance. If you don't believe that the variances are equal, maybe you shouldn't pool them together, right? But if we can assume they're equal, then we can create one estimate of the population variance. So how could we do that? Our pool estimate of the mean was in 1 mean 1 plus in 2 times mean 2 all over in 1 plus n 2. So this was our pooled estimate for the means. What's our pooled estimate for the variance?
Assume equal variance. So there are not people that you assume that they're equal.
We're assuming that they're equal.
So we presume that.
So think about what some pooled estimate means, right? Before, when we took the mean, we said that we have some population, right? And both of these samples were from that population. Now, if we want to get a better estimate of what the true mean is, let's pool those means together, which are both estimating the same thing. So here, it's sort of a similar idea. If we have one population variance, and we have two samples that we believe have that same variance, then we can pool them together. If we don't think that they have the same variance, then if we pool them together to get a better estimate of what the true variance is, that wouldn't make sense, because we're not assuming in that situation that the variance is the same, right?
So it's gonna be n1, n2 multiplied by 2 variance.
N1, N2.
Multiplied by 2 variance because we are estimating, assuming that the variances are equal, so it's 2 variances here. And
But think, for here, like we're assuming that the means were equal, but we had different estimates of what the means were, right? So we're going to have different estimates of what this is.
it's the same, we just replace it.
Just the same, just replace it, like that. So N1 times the variance for our unbiased estimate of the variance for our first sample, plus N2 times the unbiased estimate of the variance for the second sample, all divided by N1 plus N2. Does that make sense? Yeah?
It's the same thing, you give it more weight to the variance with more sample size.
That's right. You want to give more weight to the variance that came from more sample size, from a larger sample size, right? So that's absolutely right. We want to weight the one that has a larger sample size more. However, this actually is not the right formula. Why? This is very close to the right formula. So don't say, oh, this doesn't make any sense. It will make sense. It's so close to the right formula. There's just one difference. That's a hint. One difference. Plus one plus, has to do with adding or subtracting the 1. Think about the biased estimates of those. When we have biased estimates, we were dividing the sum of squares by n1 and n2, right? We were saying, okay, we have the sum of squares, and we're going to divide it by the sample size, and that's our estimate. And then we demonstrated that this is actually a biased estimate. So if we treat those sums of squares as if they had n1 pieces, this was actually a biased estimate. So what did we do? How did we treat?
n-1.
We used n-1, right? When we treated the sum of squares as if it only had n-1 pieces, then we got the unbiased estimate, right? Yes?
I mean, it's already derived from n-1, so we already did that. And it's unbiased anyway, because it was biased, then we divide it, then it became unbiased. So,
Right, but so when we took the means, like we have 30 pieces for this and 30 pieces for that. And, I'm sorry, 10 pieces for, 20 pieces for one, 10 pieces for the other, and 30 pieces total. But for this, we aren't using the n pieces. We're treating them as if they have n-1 pieces. Right? You don't get it.
I mean, 9%, because, the standard is when we did the operation already, we just divided by n-1. So, does it make a difference when you want to multiply by n?
Okay, so what he's saying is this is really the sum of squares divided by n-1, right? So this, we've already taken care of this n-1. So we don't need to include n-1 here, right? Now, if we look at this formula, if we were going to argue this similar type of thing, we would say, well, this is just the sum. So it's not a sum of squares, it's just a sum divided by n. So we don't need the n's in here because we already have it taken care of.
No, I'm just saying we don't need the n-1. We need the n, but not the n-1, because it's unbiased already.
Right, well, this is unbiased, but when you want to weight something, you need to weight it by the amount of stuff that goes into it. right? If I have, imagine that I have 2 students that got an 80 on the exam, and 1 student that got 100 on the exam. If I want to create the mean, if I just sum up these 2 pieces and divide by 2, I get 90. But I can't do that because I have 2 students that got an 80, right? So since I have 2 students that got an 80, I need to add in 2 pieces. I need to weight it appropriately. Does that make sense? Basically, the idea is that we want to weight our estimates by the amount of stuff that goes into our estimates. And when we created our unbiased estimate, we said our unbiased estimate, it's like our biased estimate, but only n-1 pieces as opposed to n pieces. So since we are treating the unbiased estimate as if it is made up of n-1 pieces, then we need to weight these instead of by n, by n-1 and n2 minus 1. And these then should be n1 minus 1 and n2 minus 1. Because that's the amount of pieces that go into our unbiased estimates. So, restating, our biased estimates had that many pieces, our unbiased estimates only had those many pieces. If we were to draw a sample mean of 1 for the first one, right, we could also get a sample mean of 1 for the second one. We could get this sample with a mean of 0.5 for the second one. We could get this sample with a mean of 0.5 for the second one. Or we could get this sample with a mean of 0 for the second one, right? So these are all of the possible second samples for just one of the initial samples. And we also have the other initial samples then there. So let's take a quick look at this. So the mean of differences between means is 0. Okay, if you look, if we count up all of the ones, we have 1, 1. And that's balanced with 1, negative 1. The zeros, let's see, we have, well, the zeros aren't going to contribute. Let's see how many 0.5s we have. We have 1, 2, 3, 4 0.5s. We also have 1, 2, 3, 4 negative 0.5s. So the differences of these is just going to be 0. Now, before, I said we had half of the differences are 0.5 away and half are 0 and half are 1. So let's take a look at how many differences are half away or 0 away or 1 away. So if we look at all of the potential differences, we have 16 potential differences. We have 1, 2, 3, 4, 5, 6, 7, 8. So half of them are 0.5 away. Now, I am lumping the 0.5s and the negative 0.5s together here because when you square them, they will give you the same thing. Okay? So we have, again, half of them are 0.5 away. How many are 0 away? Well, before we had half of them were 0 away. Now how many do we have? We have 1, 2, 3, 4, 5, 6. It's not half. 3/4. Or no, not 3/4.
7, 8.
3/8. 3/8, right? So 3/8 of them are 0 away, and how many are 1 away? 2 of them are 1 away. So, do you think that the variance of this sampling distribution of the difference between means is going to be larger or smaller? Larger. Why?
Because 1 is adding more.
Yeah, before, half were 5s, half were 0s. Here we have halves were 5s, but now we have some that are 1s. So this should give us a bigger estimate of the variance. So if we do this, so 8 times 0.5 squared plus 6 times 0 squared plus 2 times 1 squared all over 16, our answer is 0.25. 0.25.
It's the same as the first one.
It's the same as it was in the first one.
So it's not the add as well.
Well, let's look at what we're adding. So I said that this should be this, the standard error, or the sample, the variance of the sampling distribution of the means for our first sample plus the variance for our sampling distribution of the means for the second. Right now, the variance of the sampling distribution of our means was this, right? 0.125. Now we had one sample of size 2, which had this sampling distribution. We also had another sample, size 2, with exactly the same sampling distribution. So what I said is we can add those variances together. So add this one plus the one from the other one, which is exactly the same. So notice here, these aren't estimates. Those are the population because in this situation we know the population. So this divided by the sample size of 2, this divided by the sample size of 2. Well, that's just 2 times the population variance, which was 0.25, divided by 2. So these 2's are going to cancel out, and we're left with 0.25. Right? So maybe this is just a special case. I took 2 identical sample sizes. So let's try a different sample size for one of our samples to see if this is still giving us that. All right. So if we have one sample size 2, we could get 1 and 1, we could get 0 and 1, right? So here we have 2 observations of the 1 and 1, 2 of the 0 and 1, 2 of the 1 and 0, and 2 of the 0 and 0. If we take a sample size of 1, for the second sample, we can only observe either a 1 or a 0, right? Because the population only has a 1 or a 0 in it. So I draw a sample, I get a 1. What's the mean? 1. I draw another sample, I get a 0. What's the mean? 0, right? 1 divided by 1, good. So I subtract every possible second sample mean from every possible first sample mean. Okay? So I have the difference between these. So I have a 0 here, 1, this is the mean of 1, minus 1 is 0, 1 minus 0 is 1, 0.5 minus 1 is negative 0.5. 0.5 minus 0 is 0.5, 0.5 minus 1 is negative 0.5, 0.5 minus 0 is 0.5, and so on. So these represent the differences between the means. Now again, the mean of the differences between the means is 0. Zeros aren't going to factor in, but let's make sure. So 1 balances out with negative 1, and we have 2 positive 5s balancing out with 2 negative 0.5s. So our mean of the differences between means is 0. So we've got 4 that are 0.5 away. We have 2 that are 0 away, and 2 that are 1 away. So we can calculate the variance of this sample distribution of the difference between a mean with sample size 2 and a mean from sample size 1. 4 times 0.5 squared plus 2 times 0 squared plus 2 times 1 squared over 8. That's 0.375. Now, earlier I said the variance of the difference between means equals the variance for the sampling distribution of the mean 1 plus the variance for the sampling distribution of the mean too, right? So let's figure out what these were. So these are the same things. These are 0.25, right? Because this is just a population variance. 0.25, 0.25. What's n here? This is 2. What's here? What's our sample size for our second sample? 1. So that's that. This first piece, well, that's just 0.125, which is the standard error of the mean with the sample size of 2, and 0.25, which is the standard, excuse me, the variance of the sampling distribution of the means with the size of 1. I don't remember if you guys remember this, but originally when we talked about the sampling distribution of the means, we said that when you have a sampling distribution of the means with a sample size of 1, it's just the original sampling distribution, right? Which is why that has that second piece. So, cool. So we've used 2 demonstrations to demonstrate that this is correct. Now again, this may just be, something lucky that happened when I used the binomial for both of these. If you're interested, you can create your own sampling distributions in R and verify and make sure that this actually works out, and it will. Okay, so if we want the standard error of the difference between means, we just want the square root of this, right? That should give us the standard error of the difference between means. So there it is. Notice no square term here, just this. Since we are using samples to estimate, we probably shouldn't talk about the population variance. Instead, we should talk about the estimated population variance. When I did those binomials, I knew what the population variance was. But when I don't know what the population variance is, we just add these estimation symbols using our unbiased estimators to come up with the appropriate thing. So these last terms, these are unbiased estimates of the variance divided by the sample size. Right? These are each the variance of the sampling distribution of the mean. So we can rewrite it like this. Now I've introduced some new notation here. P. What do you think the P is for? Pool. P is for pool. Is that what you said? What did you say? Probability. No, it's not probability, it's pool. It is pool, that's right. It's pool, because we had 2 estimates of the variance. 2 estimates are better than 1. Let's pool them together if we can assume that the variances really should be equal. So we've got our pooled estimates of the variance divided by the appropriate sample sizes. And now I have this D here, because I'm too lazy to write the difference between the means. That's what this D is, basically the difference between the means, okay? Because really, reading this stuff in PowerPoint really sucks. All right, so, groovy. We now have a standard error, not of the means, but of the difference between means. Now we are ready to calculate.
Make a test.
What?
Make a test.
Yes, what test? A t-test. We have enough information, now we can do our t-test. We're doing an independent t-test because we took 2 independent samples. We took 1 sample, then we took another sample. Independent of the first one, right? Now you're into it. Okay, so let's go through examples. So we have sample 1, it has a mean of 79, it has an n of 49, it has this unbiased standard deviation. of 8. Sample 2 has a mean of 76 and an n of 36 and our unbiased standard deviation of 7. We have all the information that we need to know to calculate a t-test. Because now we know how to pool variances. Now we know how to create a standard error of the difference between the means. Woo! All right. Say the null hypothesis is that mean 1 equals mean 2. Alpha is going to be 0.5. All right, so let's get started. Let's pool our variance estimates. So how do we pool our variance estimate? What's the formula?
The mean first.
We don't actually need to pool the mean. When I pulled the mean, that was an example to sort of give you the intuition behind why we were doing the n minus 1. But we don't actually need to pool the mean.
What do we do? How do you figure the mean of the means?
Well, we don't need to calculate the mean of the means here. We need to calculate a difference between means, right? What's the difference between the means?
0.
No.
3.
3. Yeah, the difference between the means is 3. If you subtract the second from the first. Yes. That's what we're testing. Is this difference of 3, is this statistically significant? Is this atypical, given the variability within the population? Right? So we need to estimate the variance in the population. We have 2 estimates. Let's assume that the variances are equal and pool our variance estimates. How do we do that? How do we create this pooled estimate? Because it was the pooled estimate that we had here. Right? It's a pooled estimate. So how do we get that? I really don't want to go back all those slides.
n minus 1, n1 minus 1 by 8. No, 8 squared.
Beautiful.
So then n2 minus 1. So that's n2 minus 1 multiplied by 7 squared. So a1 plus n2 minus 2.
Çok güzel. Aferin sana. That's right. So if we do this, it's 48. So we had 49 minus 1 is 48 times 8 squared plus we had 36. 36 minus 1 is 35 times 7 squared. All over 48 plus 35. Right? Yep. So that is this. 57 change.
What do we do with this?
What do we do with this? That was going to be my question. Okay, now we have the pooled estimate of the variance. What do we do with it? Yes?
We have to figure out the standard error of differences.
Now we can figure out the standard error of the differences between means. Exactly. Yes, how do we do that?
We got the formula.
The formula? What's the formula? So fill it in for me.
So we got but we got this here we need that in as well.
We need the n as well.
Because
So
we spoke about this and this to just make it in 1 and 2.
make it n1 and n2. Would you like me to redraw this? So equals, we have p over n1 plus p over n2. Is that what we were looking for? How did you know that? There. Groovy. All right, so we have this. Now what do we do? Let's put in the values.
So 57.
57, I'll just say 0.7
Okay, 49
over 49. Not 48, over 49. This is it. Good. Yes. Plus,
plus 57.7.
same dang thing,
Over 8.
over
Wait, 36.
36. Take the square root of that. Groovy. All right. Now what do we do? So we answered what we did when you asked us what we did. So now that you have your answer, what do we do now?
Could you make it a confidence interval or something?
We can make a confidence interval.
We have t-values, critical t-values.
We figured out the critical t-values.
Then we can just make what we observed, is it beyond the t-values or not? Then we can reject or not.
Okay, you guys want to do that? You guys want to do that? That was not what I was going to do, but we could do that. And we would get the same answer. What was the t-test? I mean, to get the t-test, we needed the standard error on the bottom, and then we needed sort of like what we were predicting on the top minus stuff, right? So our one sample formula for t was this. The mean that we observed minus the hypothesized mean divided by the estimated standard error of the mean, right? Now we don't have one mean that we're testing against the hypothesized mean. We have two means that we're testing against one another, right? So how might we modify this formula?
First x minus the second x?
Whoa. Does that mean?
Okay.
Okay. So,
First x minus the
like that. Okay. That'll be a numerator. What will we use for the denominator?
The difference, the standard.
Standard error of the difference between means. D. Holy cow, you should be teaching this class. He's absolutely right. Groovy. So, what is this? What was x1 minus x2, or the mean of our first sample minus the mean of the second? It was 3. All right, so we have 3 divided by 6. Yeah, something like that. Good. Well, that's our t-value. Sweet. What do? Do we reject the null hypothesis? Do we fail to reject the null hypothesis? Do we not know right now? We don't know yet, right? We need to compare the t that we observed against some critical values for t, right? Now, if we were going to have created the confidence interval, we would create a confidence interval around our observed difference using the standard error of the differences. We also need the critical values of t there to figure out how much we multiply those by. And then we would want to see if 0 fell within that confidence interval, right? Because 0 is our hypothesized difference between means. Okay, so this is our t. We need to compare it to something. One more trick. Now we have different degrees of freedom. We're estimating 2 means, right? When we were estimating 1 mean, how many degrees of freedom did we have? We had n minus 1 degrees of freedom when we were estimating 1 mean. And we're estimating 2 means. How many degrees of freedom do we have?
N minus 2.
N minus 2?
N plus 1, N1 plus N2 minus 2.
N1 plus N2 minus 2. So we have n minus 1 degrees of freedom for the first mean, and n minus 1 with a different n degrees of freedom for the second mean. So total degrees of freedom is the n1 minus 1 plus n2 minus 1, or just n1 plus n2 minus 2, right? Those are algebraically equivalent. So these are the degrees of freedom we have for the first sample and for the second sample. So our total degrees of freedom, we just add those puppies up. Or if we were to write that differently, that would be n1 plus n2 minus 2. The same Cool. So if you remember, our pooled unbiased estimate of the variance had 83 in the denominator. That was when we estimated the variance. We had, what was it? It was 49 minus 47? No, 48. Right, that was our n minus 1. And this was 35. And we had 48 plus 35. And this is 83. Cool. All right, so our critical t-values. We can just use our quantile function in R to find the critical values for t using 83 degrees of freedom. And we said alpha was 0.05. So for the upper critical value, it's going to be 0.975, right? The quantile that cuts off the bottom 97.5%. And the lower one is going to equal 0.025, the quantile for that cuts off the bottom 2.5%. Or we could just get the quantile for one of them, and we know it's symmetric, and we've got both answers. We just add and subtract that to get the appropriate value. So here's our critical value or our critical values of t, plus or minus 1.9 and change. Our observed t was 1.8. What do? Fail to reject. Why?
It doesn't go beyond.
Doesn't go beyond. If we were to draw our distribution, which I encourage, right, we're saying it needs to go beyond 1.9 stuff and or negative 1.9 stuff, right? It needs to fall over here. But it doesn't fall in these tails, it falls like here at 1.8. So, fail to reject. That's exactly right. Now you can find p-values exactly the way that you've been doing before, except you use 83 degrees of freedom instead of what you were using before. The confidence intervals are a little different. We could figure out confidence intervals for each of the means that we observed, but our test is really not to find out what this mean is or what that mean is. It's to find out what the difference between these means is, right? So in order to do that, we can calculate the confidence interval using 83 degrees of freedom, the observed difference between the means, which here was 3, and the standard error of the difference between the means. When we were finding the confidence intervals for just a mean, we would use the degrees of freedom for that particular sample size, with that particular sample standard error of the mean. But now we're looking for the difference between the means, so we use those instead. So this part, this is our difference between the means, that's just 3. Our critical t-value, we found that in the last step. That was this times the standard error of the difference between the means, which we found earlier, which was that. So those are our confidence intervals. And what do we see about them? Does 0 fall within or outside of that confidence interval? It falls within, right? 0 is above this. So yes, 0 is in here. So we, again, would fail to reject. Yes? Okay. So, our independent samples formula. Remember earlier I had an asterisk? So we're going to see why I had that right now. What if we predicted a difference of 3? Earlier we predicted a difference of 0. We didn't have to predict a difference of 0. We could have predicted a difference of 3 or 5 or anything that we had some theory to use that in our prediction, like the jolt versus Coke amount of caffeine, right? Let's review the one sample formula. So the one sample formula was like this. Now, in the one sample formula, the predicted mean is up here. In the independent formula with the asterisk, we had this. And we don't have the predicted difference up here. The reason that we didn't have the predicted difference up here, in this case, was because the predicted difference was, what do we predict the difference would be in our null hypothesis? Mean 1 minus mean 2 equals 0. We predicted no difference, right? So if we predicted no difference, like that would sort of just drop out. Let's fix this so we have a more general formula that we can use when we're predicting the difference. So the general formula for performing an independent t-test is this. It's basically the same thing we had before. The denominator is the same. This first part is the same. The only thing that we have different is this, which is our hypothesized difference. Okay? So for a null hypothesis of no difference, that's just 0. Doesn't factor in. Now, if our null hypothesis were that the mean difference really was 3,
0?
we would have had 0 for our t-test, right? Because our observed difference is 3, and the predicted difference is 3. The difference between what we observed and what we were predicting, that's basically what we were doing here. The difference between what we observed and what we were predicting is 0. What would we have done? You don't even need to calculate critical t's. If you ever see a t equals 0, you should know to fail, to reject. What's the p-value?
0?
Not 0. No?
1.
1. What's the probability of observing a difference between means as or more extreme than no difference? Well, any difference is more extreme than no difference, right? So if we were to draw out the distribution, that contains everything. So it would be 1. Perfect. Fail to reject. All right, warning. T.test can do independent t-tests, but you're probably not going to get the same answer because what I told you is that you should assume that the variances are the same. Now, at least my version of R, it automatically assumes that they're not the same. So I will show you guys on Friday how to tell it to assume that the variances are the same. If you use help in R, you might be able to figure this out for yourself, or if you poke into my R code, you can probably figure this out for yourself. But otherwise, we'll show you how to do this on Friday. So just be warned, if you try to solve the homework using t.test, if you don't know how to set the variances to equal, you probably will not get the right answer. Now, why don't I show you how to do the unequal variances? Because it is a pain in the butt. I mean, it's easy, but like, this is really easy. This, the other way, is less easy. So if you're having difficulty with this easy stuff, like this less easy stuff would be hard. So we're just going to skip that. And you can learn about it in graduate school, or you can come to my office hours and we can have a chat. All right? All right, next class, we'll do paired t-tests. It'll be our last type of t-test. Woohoo! It's about a question of differences between means. Instead of having independent samples, you have paired samples. And maybe you act as your own control. Fun